All right, so continuing on defining aromatic systems, our systems could be aromatic, which means that they're unusually stable. So we're going to call this very stable. They could be non-aromatic, which then, is just regular amount of stability. And then there's one more thing it could be. It could be what's known as anti-aromatic. And anti-aromatic is basically the opposite of aromatic. Instead of being very stable, these are very unstable. And aromatic and anti-aromatics have very similar qualities, except for one main difference, right? Both aromatic and anti-aromatic systems are flat molecules containing a continuous ring of conjugated pi bonds. Right, so they all have this continuous ring of conjugated pi bonds. A non-aromatic system doesn't have one of these left things. Right, and it just has to miss one of them. So maybe the molecule's not flat, then it's not aromatic. Maybe it doesn't have a continuous ring of conjugated pi bonds, then it's not aromatic, right? That kind of thing. So it has to be continuous pi bonds, and they have to be rings as well. The difference between aromatic and anti-aromatic is the number of electrons. So for example, the aromatic compounds will always have the 4n plus 2 pi electrons, whereas the anti-aromatic will have 4n pi electrons. So this difference of 2 electrons determines whether it's highly stable or highly not stable. And so let's go ahead and take a look at our benzene ring first. Right, and so what you can tell is each one of these carbons is sp2 hybridized, and so we have pi bonds, and you can tell it's continuous, right? You can go around this ring in a continuous fashion. They're all sp2, so it's nice and flat, and if you count the electrons, there's 6 pi electrons, which makes this an aromatic compound. It doesn't necessarily have to just be one ring. If you combine 2 benzene rings in this type of fashion, this will be naphthalene. And again, here we have this continuous pi orbital overlap, right? If you think about all of these carbons, they're all sp2 hybridized, and so they have a p orbital. And so you can think about the electrons just conjugated throughout this whole complex. And if you count the electrons here, there's going to be 10 of them, or 5 pairs, and so this is also aromatic. If we think about cyclohexadiene, here we have these hybridized or sp2 hybridized orbitals, so we have empty orbitals, but these two over here are not sp2 orbital hybridized, and so we don't have the continuous pi orbitals, right? So there's no continuous ring here. And so this one is simply non-aromatic. If we think about hexatriene, right, we've got a continuous system here, right? We've got all these p orbitals, however, they're not cyclic. And so again, this is also non-aromatic. Let's think about some other cyclic conjugated systems. So here we have this square, right? 4 carbons, 2 pi bonds, right? So we have this continuous loop of p orbitals. However, if we count the electrons here, we end up with 4 pi electrons. And so this fits into anti-aromatic. And so this means that this compound is highly unstable. And so in the purposes of our class, we'll call this compound unstable, or we'll call it anti-aromatic. However, in real life, these compounds will try to do something to escape this aromaticity. And so what they often do is they often change shape. And so this will actually change shapes to elongate one of our bonds and to basically make this two isolated pi bonds, right? And so if you're thinking about, well, wait a second, these are highly unstable. Why do they exist in the first place? They generally don't, right? So on our piece of paper, we're going to call this anti-aromatic, but in real life, it's not going to be very stable. And so it's going to try to change itself somehow, try to react somehow, get away from this anti-aromatic unstable state. Let's go ahead and take a look at our stop sign here. So we have 8 sides, and then we're going to put these alternating double bonds. So we've got the cyclic structure. If we count our electrons, we have 8 pi electrons. And so again, this compound would be anti-aromatic. Right, and so that would be highly unstable. And so in real life, it's going to try to escape this anti-aromatic, highly unstable state. And in this case, what it's going to do is basically change its shape, right? It's not going to be flat. It's going to go to this non-flat structure, which will keep the p orbitals from overlapping with one another and basically isolate all of these pi bonds. And it's going to turn itself into a non-aromatic compound. But again, for the purpose of our class, if you see the structure up top here, we're going to call that anti-aromatic. If you see this structure down here, that's obviously non-aromatic because it's not flat. Another example right here. Again, we've got this cyclic structure, all these pi bonds, but now again, we have 8 pi orbitals, or 8 pi electrons, my bad, 8 pi electrons, and so it's anti-aromatic, which means it's highly, highly unstable. And so this compound is unstable at above negative 100 degrees Celsius, right? So you can tell that you can only isolate this at very cold conditions. As soon as you put some energy into it, it's going to go into a more stable state. So be able to identify whether a compound is aromatic, non-aromatic, or anti-aromatic.